The other day, I was talking about Fab 5. And Fab 5 stuff gives us meters per second velocity. Gives us displacements measured in meters. It gives us time measured in seconds. And it can give us accelerations in meters per second squared. In our unit on forces, those don't go anywhere in our forces. Well, most of those don't go anywhere in there. If I give you a distance, it doesn't go in Newton's second law. If I give you a time, it doesn't go into your F of G equation. The connection between Fab 5 is acceleration that gets us into forces, or forces through acceleration gets us to Fab 5. So Newton's second law says that sum of all my forces is equal to F net, which is equal to mass times acceleration. And those are some things that we can use. And when we start looking at, if we can go back to this sheet, and we can talk about, oh, well, Newton's second law is the sum of all my forces, which equal to mass times acceleration, where we add our rights, we subtract our lefts, or we add our ups and we subtract our downs. So, when we look at question number 1 on the in-class Unit 4 worksheet, it's called, and we look at the first question. The first question reads something along the lines of, a 12-kilogram crate is pushed from rest on a frictionless roller belt for a distance of 0.8 meters with a force of 36 newtons. Now, if we look ahead, A, B, and a C, what is the acceleration? What is the final velocity? How long was it pushed? All three of those questions can be answered with a Fab 5. So, probably the easiest approach to this would be, what if we only looked at Fab 5? If I were to say we have a delta x, a vi, a vf, an a, and a t, do we have enough information to solve for it? Because that'd be the easiest. Chances are not great in a unit on forces that we don't do anything with forces, but hey, it's worth a shot. So if we go through and read that problem, we're looking for distances, we're looking for velocities, we're looking for accelerations, we're looking for time. What numbers can we pull from the problem that are Fab 5 numbers? 12-kilogram crate is pushed from rest on a frictionless roller belt for a distance of 0.8 meters with a force of 36. Let's maybe start with what numbers can't go in a Fab 5 from this. Which numbers in the original part do not go in Fab 5?
36 newtons.
36 newtons do not go anywhere in here. 12 kilograms, mass, does not go in Fab 5. So what numbers do go in here then? We got a distance of 0.8 meters. There's one other number that's given indirectly.
Initial velocity is 0.
Because it starts from rest. Is that enough to do a Fab 5 problem? No, we need 3 numbers. Okay, so we don't have enough information. The way we can get to do a Fab 5 is we need one more, and generally speaking, that's going to be through acceleration is our connector to get us between that and forces. So if we don't have enough information, then we got to start looking at forces. And a good place to start with forces is a free body diagram. I have a 12-kilogram block that's being pushed from rest on a frictionless surface for a distance of, with a force of 36 newtons. So if we do a free body diagram, what forces are acting on my object then?
Gravity.
We have a normal, we have gravity, good, I heard both those, and we have applied. Are there any others? Nope, not in this problem. So, those are the forces by name. Now some of these we may need to know, and some of the, like the values, some of them we don't need to know. What's the number given in the problem? 36 newtons, where does that go? Which one of these 3 is that?
Applied.
That's our applied force. So this is 36 newtons. Now, if this object starts at rest and is being pulled to the right, is that the x or y direction? X, good, x direction. What's true about this crate in the y direction? is the velocity of this crate in the y direction constant or changing? Is the velocity up and down constant or changing? It's constant, right? And what is the velocity in the y direction if it's being pulled this way? It's 0, and it's not changing, and its acceleration is 0 in the y direction, which means my forces in the y direction are balanced, which means my ups minus my downs have to add up to 0. So when we try to determine this acceleration is in the x direction, which comes from the x direction. We don't actually need these values for this particular problem. Just to remind you, f of g is equal to weight, which is equal to m times g. So my f of g is going to be 12 times 9.8. And 12 times 9.8 is going to give us the weight, or the force of gravity, of 117.6 newtons. This is 117.6 newtons. And I'm not going to lie to you and say that's useful information for this problem. It's not bad practice to get into, but it's not something we're going to directly use in this problem. But to reinforce the idea, what's true about my forces in the y direction? They're balanced or unbalanced?
Balanced.
So what, add my ups, subtract my downs, have to be 0. So what minus 117.6 is going to give me 0? 117.6, right? My forces in the y direction are balanced. And we don't actually use those, but again, it's not bad practice. We will be using them soon. So there's two ways we can find acceleration. Fab 5 didn't have enough information, or we can look at Newton's second law, and we can solve for it that way. Now, just to be clear, this is all in the x direction. The sum of all my forces in the x direction is equal to the F net in the x direction, which is mass times acceleration in the x direction. Going back to this sheet, when we sum up all of our forces, we can set equal to F net, or we can set that equal to m times a. I'm trying to solve for that a. I add in the x direction, I add my right, so I'm adding my forces to the right. I subtract my forces to the left, which there aren't any. Maybe not a necessary step to minus 0, but it's putting it there anyways. And that's going to equal mass times acceleration. This step, well, you say, well, it's obvious right now. There's going to be more forces that get put there. It's good. It's worth the 10 seconds it takes to do it. So now that I've identified all my forces by name and what I'm going to do, add versus subtract, now we can plug in numbers. And we end up with my applied force, 36, is equal to the mass, 12, times a, so my acceleration in the x direction is 3 meters per second. So in order to find this acceleration, we didn't have enough Fab 5. We could use Newton's second law to solve for it. My forces are unbalanced. Which direction are they unbalanced? To the right, which means I'm going to have an acceleration to the right. Part B now asks, what is the final velocity Part B is asking, what is the final velocity of the object? Final velocity can only be determined with a Fab 5 problem. But now that we've determined acceleration, Newton's second law, I can use that acceleration, because it's still an acceleration of that object, in my Fab 5 list. And I can go through and I can say, well, now I want to solve for final velocity, and I don't know, and I don't care about time. So equation number 4, we probably have to pull out that equation sheet again. Final velocity squared is equal to my initial velocity squared times 2 times a times delta x where my final velocity, my initial velocity was 0, so 0 squared is 0, so my final velocity is equal to 0 plus, which we can just get rid of the 0, 2 times 3 times 0.8. My final velocity squared is going to be 4.8. But that's not my final answer, because that's final velocity squared. So we take the square root. Remember, anytime we take the square root of a number is the plus or minus choice. And when I go through and I take the square root of 4.8, I get plus or minus 2.19 meters per second. Now we gotta make the choice. Is it the plus or is it the minus? Now, I have unbalanced forces in which direction? To the right. So which direction is my acceleration gonna be? To the right. Positive. So I had a positive acceleration to the right, and I started at 0, so it means my object is going to speed up to the right. My final velocity is going to be the positive velocity. Okay. Part C, it's a different FAT5 problem. I'm not going to do it. How long would we push for? We'd solve for time. That's really the only difference there, is we're solving for t. It's a different FAT5. All right, let's take a look at number 3. In class, unit 4, question number 3. In class, unit 4, question 3 says, what is the force required to lift a 20 kilogram crate, 20 kilogram box at a constant velocity? So, if we start 20 kilogram box, what is the force? What is the force required to lift a 20 kilogram box at a constant velocity? So let's quick talk forces. What forces are acting on this box? We have force gravity, straight down towards the center of the earth, always. What else? What's that? Someone said something. There's an applied force. Which direction is my applied force? Because I'm lifting it, right? So there's an applied force. Anything else? Is there a normal force?
Yeah.
If I'm lifting my computer, is there a normal force?
No.
No, because it's not sitting on a surface. Now there's a normal force because it's sitting on a surface. Now, a slightly different way a question like this could be worded would be, what would be the minimum force required to lift the 20 kilogram box? Be a similar approach to this, but we'll talk about that in a second. Now we can go through and we can calculate F of G by simply taking the mass of the object, 20, times our gravitational acceleration on Earth, 9.8, and our F of G is equal to 196 newtons. What's true about my normal force? Well, what's true about my acceleration? What's true about my F net? What's true about my forces? Are they balanced or unbalanced? So let's start with, are my forces balanced or unbalanced? I'm lifting this box. Okay, if they're unbalanced, how do we know they're unbalanced? Or if they are balanced, how do we know if they're balanced? Let's go back to the acceleration. What's the acceleration of this thing? How do we know it's 0?
This is constant velocity.
It says constant velocity. So it says constant velocity, which means my acceleration is 0, which means my F net then is 0, which means my forces are, what is that? If my acceleration is 0, my F net is 0, that means my ups minus my downs have to add up to 0. What's true about my forces? Are they balanced or unbalanced? If they have to add up to 0, they're going to be balanced. They're going to be balanced forces, okay? So the long way is to say the sum of all my forces is equal to F net, which is equal to mass times acceleration. We can say acceleration is 0, or we can say my F net is 0. Newton's second law says that when I add my ups and I subtract my downs, they have to add up to 0. We can then say my applied is equal to my gravitational. So this is also going to be 196 newtons. Now, what does constant velocity look like when I'm lifting an object? It could look something like this. That's a relatively constant velocity. This is also a constant velocity. Now you could say, well, are you lifting it or are you holding it? Yeah, you're probably right. You're probably holding it. But the idea is that would be the same force diagram, whether I'm lifting it or I'm holding it. Both situations, no normal force. And in both situations, I have a net force is 0.
I hate to interrupt, but can I have like 1 minute?
Okay, so that's what we talk about when we talk about forces. Now, slightly different wording of this question, like I said, could be, is what is the minimum force needed to pick something up? So if we go through and talk about like minimum forces that we could pick something up with, let's pretend for a second that my computer weighs, I don't know, 5 pounds. Sure, 10 pounds. We'll go with 10 pounds. If I were to take this computer and I were to pick up where it's on it, and I lift with 4 newtons worth of force, did this thing move? No, right? Because I didn't apply a big enough force to it. Okay, what if I go 8 pounds? Remember, it's 10 pounds. Lift up with 10. Are my forces balanced or unbalanced right now? They're balanced. They are balanced because my velocity is constant. My up is 8. My down is 10, which means I have to have my normal force is 2, right? Because the table's still pushing it. What about if I lift upwards at 10 and my computer only weighs 10? My force is balanced or unbalanced? Up 10, down 10. Those are balanced forces. My computer moving yet? No. So in order for me to get something to move, I have to apply a slightly larger force than that. Whether it be 10.1 or 12, I don't care. It has to be bigger. Once I get this going, yeah.
So then why would the answer number 3 be 196 if it's the same as the first?
What's that?
You said the force
Yeah,
required to
because the
lift.
force is the same then.
So then why would it be more?
Are we talking about number 3 right
Yeah.
now? Or are we talking about my computer right
Number
now?
3.
The number 3.
Number 3? So why are my forces what?
Why wouldn't it be more than 196?
Oh,
Answer.
because what did it say the computer was moving at?
Never mind.
Right? Constant velocity, so acceleration is 0, therefore that's why.
So
I had to, initially there had to have been an unbalanced
Okay,
force.
got it.
That's where I was trying to get to, okay? So even if I lift up at 10 pounds, this isn't gonna move yet, right? So I have to maybe go 10.1 or 11, but then once I started moving, now I only have to apply a 10 Newton force, and as long as 10 pound force, and as long as I apply a 10 pound force, and my velocity is gonna count. But in order to get something to first start moving, we have to have a slightly unbalanced force. So if it were to say like, what's the minimum force required to lift a 10 pound object? It's 10.00000 something, right? You gotta go slightly different, but it's like right on that threshold of that. Okay? 2 things I want you to do. Any questions on these 2 problems before we move on? Okay, two things for the rest of today. First thing, I have a progress quiz that is just gonna go through and look at force of gravity, weights, normal forces, masses on different locations. It should take you, it's a couple minutes, it's a quick one. I have 3 answer keys posted in the back of the room, one at that table, one at that table, and one at the wooden table. Feel free to check it yourself. If you want me to talk about something or explain something with you, please, please, please ask. Please ask. It's a pretty straightforward one, so I'm not gonna make you stand in line to talk to me. But if you want, I'm more than happy to talk to you. Okay, so I'll give you one of these in a second. On the middle wood table, once you've checked your answers, there's another worksheet called Forces 2. Make sure you pick up Forces 2. That's your next homework sheet. It's due, not tonight, but tomorrow evening. Okay, so we'll have some additional time tomorrow in class to work on it. But Forces 2 looks at the connection between Fab 5 problems and forces using Newton's second law. So that's what we're doing for the rest of class today.